searching techniques, linear search, binary search, and hash. In searching technique, we are going three techniques: linear search, second one is binary search, and hash. Now let us start with the linear search. Linear search is very simple type of search technique. Now here, let us assume you are given one list for searching. Searching is one of the important operations performed on linear data structures. Rather, it is also performed on non-linear data structures like tree. So we will see how searching can be done on linear data structure as well as non-linear data structure. So our focus in this chapter is how searching is done in linear data structure like list. Suppose you are given a list having 5 numbers in it. Suppose these 5 numbers are 8, 2, 5, 3, 9. These are the 5 numbers given and these are the indexes of the elements. Sorry, this 2, 3 and this is 4 indexes. And suppose you are given number to search. So your task is to compare the given number with all the numbers in this list. And the moment you find the number at any of the location, you have to declare that the search is successful and you have to return the index of that element. Now suppose you want to perform search for the given element 3. The given element is 3 and suppose you want to search for this given element 3. So what is your strategy? Strategy is very simple. Linear search. In linear search, you have to compare given element with all the elements starting from index 0 till. So compare 3 with 8. So both are different. Then compare 3 with 2. Both are different. Then compare 3 with 5. Then compare 3 with 3. Now here you find 3 at index 3. So the search is successful. So you have to return index. Similarly, when you are given element 18 for searching, now same strategy will apply. 18 is compared with first element 8, it is not there. Then it is compared with 2, then 8 is compared with 5, 8 is compared with 3, 18 is compared with 9. So are there to compare. So it is unsuccessful search. So in case of unsuccessful search, linear search has to return -1. Why it is returning -1? Because -1 is not the index of any element. So -1, if it is written by linear search, then it indicates that the search is unsuccessful. And if any index is written by the linear search, then that indicates at that index the given element is present. Now this is the linear search. Now let us try to find out the complexity of the linear. Now you can see here, in this case, complexity is number of comparisons we are doing, both in searching as well as sorting technique. Of comparison, main key operation. Other operations are also there, but here the key operation is number of comparisons. So in linear search, we count the number of key operations like comparison, number of comparisons required. Now, when you want to search for 8, now 8 is present at first slot only. So 8 is found at first slot. So here the search stops and it returns index 0. So here in only one comparison, you can find 8. Suppose you want to search for 9. 9 is compared with all the elements starting from index 0 to 9. So this is the third comparison with the 9. So this is the fourth comparison with the 9 and this is the last comparison with the 9. So 9 is present at this slot, but you require 1, 2, 3, 4, 5 comparisons to locate 9. So if the given element to be searched is located at the last element, then you need n-1 comparisons, where n is number of elements, in the list, or you can call it as the size of the list. So in the worst case successful search. So there are in successful search there are two cases. In successful search, there are two cases, best case and worst case. So only one comparison element is present. So best case is O of best case we express in omega. So best case is omega of 1 and worst case is O of n, because total number of comparison. This n stands for number of elements. Total number of comparisons, if the given array is having n elements, is n minus 1. From Tn we can find, from Tn pick the highest order term. So this is n raised to 1, and 1 can be represented as n raised to 0. 1 can be represented as n raised to 0. So highest order term is n raised to 1. So it is given as O of n. So it is given as omega of 1. So best case complexity is omega of 1. And worst case complexity is n minus. So Tn is n minus 1. So best case complexity is O of n. So this is a higher order term. So in this way, linear search is implemented. So the implementation aspect, so the algorithm is given over here. So sequential search, linear search is also called as sequential search. So the algorithm search is given. A is the list or array in which elements are there, in which X is the element you want to search. So while loop is used, initially I is used as an index where you want to search. So if I is less than n, means all the elements, until all the elements are not searched, and a of I is not equal to x. The element at index I is not equal to x. If these two conditions fill, then you have to increment I to search for this way. Unless this one of these two conditions. So if the condition is failed due to this, when I becomes equal to n, means you have searched all the slots. You have searched all. So in that case, search is answered. And if the condition is failed due to this, so if a of I is equal to x, which means the given element is. So when the search is when this while loop is terminated, either by becoming this condition false or by becoming this condition false. When this condition becomes false, when I becomes equal to n, we have searched all the elements. When a of I is equal to x, then the given element is found. So after while loop, we have to compare due to what it has been failed. So after here we compare. If a of I is equal to x, then the element is found at index I. If that is not the case, if this is not the case, then we check whether I is equal to n. Means it is failed due to this condition. So if I is equal to n, then data not found. So in that case, you have to return -1. So this is all about linear search. The next type of search is the binary search. So in the binary search, the list. So let me explain binary search first. So first of all, we will see the logic of the binary search. It is not like a linear search. Binary search is very different. Now, suppose many of you have seen the telephone directory. How the telephone directory, we can search the telephone number in the telephone directory. So a telephone directory looks like this. So in the telephone directory, there is the alphabet C on the top of the page, and all the elements, all the entries in that page in the telephone directory are in that particular page are having names and phone number corresponding to C. So for example, Chetan, the name is Chetan, and the name is Charuta likewise. So this is having phone number, this is having 982276. This is the phone number for Chetan, 8522. This is the phone number for etc. Dot dot dot. This is the phone number for Charuta likewise. So this page is having all the phone numbers of the name starting with starting with C. Now similarly, another page on that there is a phone numbers of all the names starting with D. Similarly, there is a third page where there is all the phone numbers of the customers starting with E. Likewise, you have till Z. You have last page in which all the names start with Z. Likewise. Now here, if you want to search for the mobile number, what you do, this and suppose you want to search the mobile number of the customer starting with S. You know where this S stands for. So alphabet A, B, C, D, and so on. Somewhere it is S, S, T, W. You find it. I will show. This is the book. This is the book kept, and these are the pages of the book. So you open. This is the page A, B. This is the page C. This is the page D. What do? You don't know where there is a S. Somewhere S is there. Somewhere here. S page is here. Somewhere here in the second half. So what do? You open the telephone directory from this half. Somewhere half. When you open the first half page, somewhere that page is P, and all the pages on the left of the P are with page A, B, C, D, and all the pages on the right side of the P is Q, R, S, T. So suppose we assume that. Now you know that you want to search for the telephone of the customer starting with S. Now leave this space because they are sorted. This book is sorted based on the page number A, B, C, D. So you leave these pages and you pick this page, pick this half pages. Then again you pick the middle page. Again you pick the middle page and see what is the character on that middle page. And you want to search for S. So there are again two possibilities. The character on this page is maybe left on this left of this S, right of this. Based on that, you leave again these half pages and you consider only these half pages. Now again you open half pages character on that middle page. So in this way, you either move towards the left or right, and then you come to the particular page where you find out the name of the customer and you get the mobile number. So this is the approach we adopt when we search for the telephone directory. So when you search for a number in the telephone directory, you are actually performing the binary search. You are actually performing the binary search. Now, why you can perform the binary search in that? Because the pages in the telephone directory are arranged in the alphabetical order. Means already the pages are sorted in the alphabetical order, and names in the pages in per page. So all the names starting with C in this page are also sorted. So all the names in the page are also sorted, and all the pages are also sorted. So that's why you can apply binary search. Let me give you an example. Suppose this is the list of where these 5 elements are sorted in. Suppose this number is 2, this number is 9, this number is 12, and this number is 15. And you know that this is sorted. So index 0, index 1, index 2, index 3, and index 4. You know that this is sorted. And suppose you want to find the element 15. You want to find the element 15. Now what do? You know that this is already sorted, and you know where this 15 is present in this. You know you don't know the elements present in this, but you only know that this is sorted. Now you want to find 15 in this list. So what you can do? You have to find out the middle of this list. You have to find out the middle of the list. Now how can you find the middle of the list? This 0 plus 4 divided by 2. You get the middle index. So 0 plus 4 divided by 2. Now what you get is 2. Now 2 is the index of the middle element. So 2 is the index of the middle element. And here you compare the given element 15 with the content of the middle element, middle slot. So at middle it is 9, but what you want to search for is 15. Now 15 is not present at this index. So at index 9 is present. Now where this 15 can be present? You know already this is sorted, and you know this is 9. So all the elements on the left of this 9 will be equal to or less than this 9, and all the elements on the right side of this 9 are always greater than 9. So if at all 15 is present in this list, so it will not be present on the left of the, but there is a chances that it is present on the right side of the 9. So we'll leave these elements. Now we want to focus our attention to find this 15 on this left half, second right half. Now our list is this. Now initially our list is having 5 elements. Now our list to search is only this list of 2 elements. Now in this case, in this list, our starting index is 4 and ending index is 4. Now again you have to find out the middle of this list. So what is the middle of this list? So this is the starting index as 4 and ending index as 4. So middle is 3 plus 4 divided by 2. So what you get is 7 divided by 2. So it is 3.5. So if we consider as an integer, so what you get as an integer of 3.5 is 3. So middle element is considered as 3 only. So next you compare 15 with the middle element. Now you compare 15 with this middle element. So you compare 15 with 12. Now 15 is also greater than 12. So there are 2 possibilities. Either 15 should be equal to this, or 15 should be less than this, or 15 should be greater than this. So here 15 is greater than 12. So if at all 15 is there, it may be on the right side of this 12. So on the right side we have only with size only 1, because we have 1 elements left. So we have to focus our attention to search 15 on this list, of only 1 element. Now this is the list of only 1 element with index 4. Now we have to find out the mid of this list. Now, what is the starting index of this list? 4. What is the ending index of this list? 4. So starting index is also 4 and ending index is also 4. So mid is also 4. So 4 plus 4 divided by 2, the mid is also 4. Now this is the mid, then you have to compare the given element with the mid. So mid is 15. Now here you have found successfully the given element. So here it marks successful search and you have to return this index. This is how the binary search is done. Now I give you one more example. Now consider more number of elements. Now we consider 10 elements. Now consider 10 elements in the ascending order. Now consider straightforward elements only 1, 2, 3, 4, 5, or we consider 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we consider only 10 elements. And these are the indexes. Now you want to search for 11. Now how this search for 11 will take place? Now first of all, the list to be searched will be having 10 elements and starting index is 0 and ending index is 9. So you have to find the first mid. So first mid you will find by adding starting index with ending index, that is 0 plus 9 divided by 2. So what you get is 4.5. So actually it is 4.5, but when you consider only as an integer, it is going to be 4. Now in the element with index 4 is now considered as the middle element. Now you compare after finding the middle element, you compare 11 with the middle element. So here middle element of this 10 elements list is 15. Now 11 is less than 15. So if 11 is present in this list, it may be on the left side of the 15, and all the elements on the right side of the 15 will be more than 15, and all the elements on the left side of the 15 will be less than 15. Now we should focus our attention in order to find 11 on the left half of the list. Now we forget this big list of 10 elements. Now our next list to be searched is the list with only 4 element. Now this is the 4 element list where we want to focus for next search. Then the starting index is 0. Starting index is 0 and the ending index of this list is 3. And you have to find the mid of this list. So what is the mid? 0 plus 3 divided by 2 is 5, but what we get is only 1 as an integer. So this index element now considered as the middle element. Now again compare 11 with this middle element. This middle element is considered as 12. Now again 11 is less than, so if at all 11 is present, it may be on the left side of this 12 because it is less than 12. Now we leave this list and we focus our attention on only list on the left side of this 12. So the list on the left side of this 12 is having only one element in that, and its starting index is 0 and index is also 0. So again we find the so this is the list with only one element. So we find starting index and ending index of this list. So we find the mid now again of this list. So mid of this list is starting index is 0 and index is also 0. So divided by 2 will give you also 0. So mid is 0. Now you compare 11 with this mid element. So it is 11 and here you find the 11. And then the search is declared as successful. Its index, that is 0, is returned where that element is present. Now next we want to compare, next we want to find out element 23. We want to search for the element 23. Now, okay, now let me consider one more array for unsuccessful search. Now this is the array having 6 elements. So 11, 12, 13, 14 or 15. Suppose it is 5 elements. So these are the indexes. And you want to search for element 23. 23 is not present in this. So how you get an unsuccessful search? Now let us see. Now, as usual, the list is having 5 elements in it, and you have to find out the mid of these 5 elements list. So the index of first element is 0 and index of last element is 4. So 0 plus 4 divided by 2 will give you the mid index. So that you get is 2. So this 2 is the mid index. So this 13 is the middle element now. Now compare 23 with the middle element. Now 23 is greater than 13. So if at all 23 is present in this list, it may be on the right side of this list. This left side will avoid. So we will leave this left side and we will focus our attention on this right side. Now on the right side, the total number of elements are 5 and this index 2 is the mid. So on the right side, there will be only 2 elements present. So this is the 2 elements list that we want to search for. And the starting index of this list is 3 and ending index of this list is 4. Now you have to find out the mid of this 2 elements list. So again, you have to find out the mid, that is starting index is 3 and ending index is 4. So 3 plus 4 divided by 2. Now what you get is 7. 7 divided by 2, that actually gives you 7 divided by 2, that actually gives you 3.5. But because it is integer, we consider it as only 3. So index 3 element is considered as a middle element of this 14 and 15 list. Now again you compare 23 with this middle element. Now see, first we compare 23 with index 2 element, that is 13. Then we compare 23 with 14. Now again 23 is found to be greater than 14, right? Then we focus our attention on only this sublist. So this sublist is list with only one element whose starting index is also 4 and ending index is also 4. Now again we find out the mid of this. Now see, first starting index is 0, ending index is 4. Then we compare, we find out the mid. So mid is 12. 23 is greater than 13. Then our starting index is changed. So initially my starting index is 0. Then my starting index is changed from 0 to 3. So next starting index is 2 plus 1, that is 3. So whenever starting index change, either starting index is changed or ending index is changed based on the middle element content. So here starting index is changing every time and ending index is remaining same. See, initially the starting index is 0, ending index is 4 and mid is 2. So we compare 23 with element at index 2, that is 13. So 23 is greater than 13. So this is now our next list whose starting index is 3 and ending index is 4. So initially starting index was 0. Now starting index is 3. So next starting index was found from mid. So if mid is 2, next starting index will be 2 plus 1, that is 3. Now again here in this case, in this two elements list, this 14 is considered as the middle and 23 is greater than 14. Then again you have to find the right sublist. So right sublist is this, whose starting index is 4 and ending index is also 4. So here starting index is found by mid plus 1. So mid is 3, mid plus 1, that is 4. So starting index is 4 and ending index remains 4. Now compare 23 with 15, that is mid. So starting index is also 4, ending index is also 4 and divide by 2. So mid index is 4. So mid index is 4 and 23 is compared with the element at index 4. So element at index 4 is 15. Now 23 is now also greater than 15. Now what is our practice? 23, if at all it is there, it may be present on the right side of 15. It may be present on the right side of 15. But we don't have any element on the 15. But still, we increment this starting index. Now what will be the starting index? Starting index will be more than 4. Next starting index will be more. We search on this sublist start, but there is no sublist starting with 5, but ending index is 4. So when you increment the starting index from based on the previous mid, so previous mid is 4 and next starting index is 5. So next starting index will be 5 and ending index remains 4. Ending index is not changed, but starting index become 5. So when starting index is 5, when starting index is 5 and ending index remains 4, this is the contradictory. You can't have any list whose starting index is more than ending index. So when you consider this 5 elements list, starting index is 0 and ending index is 4. When you consider these two elements list, starting index is 0, ending index is 1. When you consider this one element list, starting index is 4 and ending index is 4. So whenever you consider any list, starting index is either equal to ending index or it is less than ending index. But starting index never becomes greater than ending index. Starting index never becomes greater than ending index. So the moment starting index becomes greater than ending index, we consider that the search is unsuccessful, which means that this 23 is not present in the list. This 23 is not present in the list. So here, using this condition, we say that the search is unsuccessful. The search is unsuccessful means this 23 element is not present in this given list of 5 elements. Now, same thing we have to implement it in two ways. Binary search we can implement in iterative manner as well as in recursive manner. So these two implementations we will discuss. Yeah. Now binary this is the recursive version and this is the iterative version. Now in iterative version, low means starting index and high means ending index. See here there are n elements. There are n elements in array A. So starting index initially will be 0 and ending index will be initially n minus 1. So if there is 5 elements, so n is 5. So ending index high means ending index. So low and high, these are the indexes. So high is ending index. So ending index will be 4 and starting index will be 0 if there are 5 elements. Now see here, this condition as I stated, low should be always less than equal to high. Means starting index should always be less than or equal to ending index. When low becomes greater than high, means when starting index becomes greater than ending index, then the search is unsuccessful. So first, if we consider whether low is less than equal to high. If low is less than equal to high, then we find out the mid. Then after finding the mid, then we compare the given element. If there are three possibilities. The given element is less than middle element. The given element is greater than middle element. If these two are not met, means either the given element is not less than middle element or the given element is not greater than middle element, then it is equal to middle element. So when it is less than middle element means this condition. So this is mid, this is mid, this is low, this is low, and this is high. So given element X, you have to compare with mid element. So suppose this is A. So A of mid, is this element. So given element X is compared with the mid element. So if it is, if the given element X is greater than mid element, if X is greater than mid element, then maybe X is present here. This maybe X is present here. In that situation, what we do, we change the low from here to here. The our next low will be here because our next list will be this list. So this is low and this is high. Means this is the index of the this low is the index of the first element in this list and high remains as it is. So next we find low. So how we find low? Low is equal to mid plus 1. So low, we change the low. Low is equal to mid 1, mid plus 1. Now another possibility is if X is less than mid element. So X is less than a mid element. So this array A. So A of, so if X is less than mid element, so maybe X is present here in this sublist. In this sublist means next you have to find out the mid of this sublist. You know the low fix, but you don't know high. So how you can find last element in this sublist? High. This is the index of last element in this sublist. Now what is the next high? This is mid minus. This is mid minus 1. High will be mid minus 1. Here low will be mid plus 1. So in this case, when given element is less than A of mid, then you have to change high. This high will come here. If this X is greater than mid element, if this X is greater than mid element, then you have to perform search for this X in this half. In this case, you have to change the low. So your next low will come from this low to here. So your low will be mid plus 1 and here your high will be mid minus 1. Same thing is explained over here. So if it is less than middle element, then you have to change the high. If it is greater than middle element, then you have to change the low. So low will be mid minus 1 and high will be mid minus mid. So it should be 1 plus 1. By mistake it is minus 1. One of this should be plus 1. So low should be plus 1 here, mid plus 1. So make the correction as accordingly. Low should be mid plus 1 and high should be mid minus 1. And third condition, when X is exactly equal to mid, when X is exactly equal to mid, means when X is neither less than mid or greater than mid, the remaining is it is exactly equal to mid. So in that situation, you have to return mid. Means the index has been found. Means element has been successfully found. So you have to return mid. So this is the iterative version of the linked list. Binary search. Now let us try to find out the complexity of this binary search. Now, suppose these are the 8 elements. 1, 2, 3, 4, 5, 6, 7, and 8 elements. So 0 and 7, 8 elements. In all, total 8 elements. And this is considered as a mid element. 4, 5, 6, 7. Now, consider 11, 12, 13, 14, 15, 16, 17, and 18. Now you have to find out the best case complexity and worst case complexity. So there are two successful. The element has been successfully found. successful search another one is unsuccessful search. In success, you have to make comparison successful, and maximum how many comparisons are required in success. Now, you want to search for 14. If you want to search for 14, 14 is present at the mid element. Initially, we find the mid element. So what is the mid of this list? 0 plus 7 divided by 2. So 7 divided by 2 is 3.5, and the integer of 3.5 is 3. So at index 3, the middle element is found. So in the first comparison, you find the given comparison. You want to find out 8. So in order to find 18, how many comparison is required? And suppose you want to find out 11, how many comparisons are required? Now you tell me. Now this is the question to all of you. You have to tell me to search 14 using binary search, how many comparisons is required? To search 18 using binary search, how many comparisons are required? And to search 11 using binary search, how many comparisons are required? Now you take up this as a quiz, and all of you tell me how many comparisons are required to find out 14, 18 and 11. Now write it in the chat box. See, remember, these are the 8 given elements. So all these 3 conditions are for successful search. 14 is also present, 18 is also present, 11 is also present. So all these 3 are the successful search. So one will be the best case, another okay, I request all the students to write into the chat box how many comparisons are required to find 14, 18 and 11. answers are for 14 1 comparison, 18 4 comparisons, and 11 3 comparisons. Okay, so many of the students have given the answer. So let us find how many comparisons are required actually for 14. So 14, first of all, we have to find out the mid. So first mid is 0 plus 7 divided by 2, that is 3. So this is the first mid. So 14 is compared with the mid element. Here the 14 is found. So it requires only one comparison. So in one comparison only 14 can be found. Now you have to find out the 18. So first mid is 14. 18 is greater than 14. Now what happens? Initially this is low and this is high. Now you want to compare with in only this list. So in this list, so new low will be 4. So it is previous mid plus 1 will be the new low. So 4 plus 7 divided. You have to find out the mid of this list. 4 plus 7 divided by 2. Now it is 11 divided by 2. Then it is 5.5. 5. Yeah, it is 5.5. So 5.5 means we consider only 5. So next mid. So first mid is 14 in this 8 element list. Now in this 4 element list, next mid is 16 with index 5. Now again 18 is compared with 16. So here there is a two comparisons for 18. First 18 is compared with 14. Then now 18 is compared with 16. Now here also 18 is found to be greater than 16. Now which means that 18 if at all is present, then it may be present in these two elements list. Now again you have to find out the low of this list. So low of this list is given by this 5 is the mid 1. So it is 6. Low of this list is 6 and high remain as it is. So now again find out the mid of these two elements. So 6 plus 7 divided by 2. It is 13 divided by 2. Now it is approximately 6.5. So it is 6. Now this is considered as the mid element. Element with index 6 is considered as the mid element. So 17 is the mid element. Now compare 18 with the mid element 17. Now 18 is also greater than 17. So here 18 is compared with 17. So this is a third comparison. So first comparison is done with 14. Then second comparison of 18 is done with 16. And now third comparison of 18 is done with 17. So this is the third comparison. Now here 7 is not equal to 18. 17, sorry, 17 is not equal to 18. Then we focus our attention on this list with only one element. So this list with only one element starts so 7. So previous mid was 6. So mid plus 1, it is low. So next low is 7. Next high is also 7. Mid is also 7. Now 18 is compared with the mid 7. So here you find 18. So 18 is now found. But 18 require 4 comparisons to found. So first comparison is with 14, second comparison is with 16, third comparison is with 17, and fourth comparison is with 18. So to find 18, we require 4 comparisons, and to find 11, similarly, we require 3 comparisons. See, first comparison of 11 is done with 14. Then 14 is less than 14 is greater than 11, means if 11 is there, it may be present on this list. Now we find out the mid of this list. So 0, 1, 2, the mid is this 2 divided by 2. So this is the mid with index 1. Now we compare 11 with 12. 11 is less than 12. So 11 is present here. Now we change the high. Low remains same. Low remains 0. We change the high. So here the high is 2. But now this is only one element list in which we have to compare 11. So our next high will be mid. This mid is 1, mid minus 1. So that is 0. So low will also be 0, high will also be 0, and mid will also be 0. Now 11 is compared with the mid as 0. So here 11 is found. Okay, so in how many comparisons we found 11? So first comparison of 11 is done with 14, that is mid of this 8 element list. Then 11 is compared with this 12, which is the mid of this 3 element list. Then 11 is compared with this 11. that is made of this one element list. So in three comparisons, we found 11. So what is the maximum number of comparisons we get for 8 elements list? For 8 elements list, okay, so we get maximum number of comparison is 4. So total number of comparisons for n number of, so for 8 elements list, so T of 8 element list, we get maximum number of is and minimum is 1. So we can write it as 4. So these 8 elements we can write it, 8 elements I can write as a log of 8 to the base 2. So that will give us as 3. So log of 8 to the base 2 will give us 3. Imagine if there are 16 elements and you have to compare the last element. So in that case, you need 5 comparisons. See here, for 8 elements, worst case is 4 comparison. For 16, worst case will be 5. For 32, the worst case will be 6. So you can write this as log of 8 to the base 2 plus 1. Then you can write this log of 16 to the base 2 plus 1. So what is log of 16 to the base 2? 4. That is 4 plus 1. Then if there are 32 elements and you want to search for the last element, so it requires 6 comparisons. So in that case, you can write this as a log of 32 to the base 2 plus 1. Total number of comparison Tn, exact number of worst when you express it in terms of Tn is given as log of n to the base 2, log of n to the base 2 plus 1, log of n to the base 2 to the base n. So this is exact total number of comparison in the worst case. And if you want to find out the complexity in big O notation, now big O of this can be represented as O of which is order term, this is the variable term. So we represent this variable term as log of n to the base 2. So worst case complexity of the binary search is given as O of log n to the base 2, and best case is given as omega of 1, because in best case you require only one comparison, and in worst case you require total number of comparisons required are log n plus 1. But when we express in terms of big O, we consider only higher order term, so that is log of n. So its worst case successful search is given as log of n, and best case successful search is given as log of 1. If you want to search for the element which is not present in this, still you require log of n plus 1 comparison, and that is given as possible search. For unsuccessful search, best case is also log of n, and worst case is also log of n for unsuccessful search, because you need more number of comparisons. So in objective exam, this complexity for successful search and unsuccessful search for linear as well as binary search can be asked. So linear search, successful search, best case complexity is 1, and for successful search, worst case complexity is n for linear search. For binary search, successful best case complexity is 1, and unsuccessful best case successful complexity is 1, and worst case successful complexity is log n. For unsuccessful search, best case is also log n, and worst case is also log n for unsuccessful search. Because if its implementation and its complexity. So binary search can be implemented iteratively or recursively. So next lecture we'll start with the next searching technique, that is hashing.